Alright, in this video we are going to cover centripetal acceleration. So let's start out with a definition. So we know that regular acceleration involves a change in velocity, and acceleration is a vector. And that means it has both a magnitude, so it has a number, and it has a direction. So what would happen if we had an object moving in a circle of radius r? Alright, and we haven't gotten to angular variables yet, but let's say it's just rotating with a constant speed. Is there any acceleration? Well, if its rotating speed is constant, you might think, well, no, it's not changing its speed, but it is changing its direction, right? Because at one point, it's here with a tangential velocity in this direction, and tangential velocity is just its velocity if it were moving in a straight line. But over here, its tangential velocity is going to be in a different direction, therefore this object has an acceleration. And this is called a centripetal acceleration because that acceleration is due to whatever force is causing it to rotate. So maybe you're spinning a string above your head, or maybe there's a force of gravity on like a planet orbiting the sun. But we say that centripetal acceleration is equal to the velocity squared divided by the radius of its path. Alright, so when analyzing circular motion, we have some tangential and some rotational quantities, and rotational quantities will be studied deeper in a different unit. But we know that our centripetal acceleration is center seeking. It's towards the center of the circular path. And that could be friction, that could be gravity, that could be tension, it can be a number of things. But then we have tangential quantities, and those are tangential to the circle. That means they only touch at one point. And that would be velocity and acceleration. Alright, and those quantities are always changing because they're vectors, and their direction is always changing. Alright, here is our first problem. So we have a car that's going to be traveling in a circular track. So let's just draw a picture to help us visualize this problem. There's our circular track. It has a radius of 500 meters. So that means from any point on the edge to the center of the track, it's going to be 500 meters. And at a particular moment, we have a velocity directed to the west. So its velocity is directed this way, and an acceleration to the north. We want to know, when viewed from above, in which direction is the car going to be moving and how fast is it going. Alright, well first let's just try to figure out where on the track it could be. So because the acceleration and the velocity are perpendicular to each other, that acceleration has to be our centripetal acceleration. And that's another thing to know, is that because centripetal acceleration is center seeking and the velocity is tangential, they have a 90-degree angle between them, and that's how I can tell that in this problem it's a centripetal acceleration, because one is to the north, the other is to the west, so they're at 90-degree angles from each other. So because our acceleration is centripetal, the car is going to be at the bottom of the track with an A in this direction and a V in this direction. Alright, so because it has a tangential velocity in this direction, that would be clockwise, so that rules out choices A and B. Now we need to figure out its velocity. Well, we know our equation for centripetal acceleration is A sub c equals v squared divided by r, and then we can solve for v to get the square root of centripetal acceleration times radius, which will equal the square root of 500 times 5, which equals 50 meters per second, leaving us with option C as our correct answer. So hopefully you got that. Alright, in our next problem we have a car moving at a constant speed over the top of a hill, and we want to know the direction of its velocity and acceleration. Well, because the car is moving at a constant speed, we were to draw our circle. That would mean that the magnitude of the magnitude of its tangential velocity is constant. Because if you remember, speed is independent of direction, so you can be moving in a circle with a constant speed. Alright, we want to know direction of velocity and acceleration. Well, based on my little drawing here, we can see clearly that it's going to be moving in this direction. Now, the easiest to figure out would be the acceleration, right? Because we can just think of this hill as a section of a larger circle, like that. So if this is going to be like the center, we know that our centripetal acceleration starts at the edge and points towards the center. So that would rule out options A and C. Now, the tangential velocity is tangent, so it touches at one point where the car is. So the car is going to be moving to the right at this moment, at this instant. A second later, half a second later, it's not moving perfectly to the right anymore. So that's velocity, that's acceleration, and that gives us option B. Alright, this will be the last problem for this video. So we have a car traveling at a constant velocity when a stone becomes stuck within the tread of a tire, and we want to know which of the following describes the initial acceleration of the stone. So this is a more challenging problem. Alright, so here we've got a stone, and it becomes stuck within a tire. Now, you might have a few thoughts here. Well, the stone is initially at rest, becomes stuck within the tread of a tire, right? So it's obviously going to begin accelerating upwards, but it's also going to be start accelerating forward too, right? Well, or more backwards, because it's going to travel in this direction with the tire. So maybe you're thinking A or B, but I want you to think about the fact that the stone is now entering circular motion. It doesn't really matter what its initial condition is, because now it is in circular motion, and that tire is providing a centripetal acceleration, right? It's at the bottom of the circle. It's going to have a centripetal acceleration upwards. So that's going to be option D. To wrap up this video, here is the challenge problem. The solution will be at the beginning of the next video, or you can find it on my Instagram page 24 hours or so after the release of this video, link in the description.